Hi folks, this is Calc 3, Checkpoint Quiz 7. Number 1, we're asked to state what it means for a function to be differentiable at the point x naught, y naught. So, f is differentiable at x naught, y naught if and only if there exists two functions, epsilon 1 and epsilon 2, such that f of x naught plus delta x, comma, y naught plus delta y minus f of x naught, y naught equals the partial derivative with respect to f at the point x naught, y naught times delta x plus the partial derivative of f with respect to y at x naught, y naught delta y plus epsilon 1 delta x plus epsilon 2 delta y, where epsilon 1 and epsilon 2 go to 0 as delta x and delta y go to 0. So that's the definition. Now if we want to look at this in sort of a bigger picture, what's actually happening here? Well, we're graphing z equals f of x, y, so that's going to result in a surface. We're looking at the point x naught, y naught as sort of our anchor point, the point we're starting at. And then we're moving some distance in the x direction, delta x, and some distance at the y direction, delta y, to give us our new point. So f at this new point represents the z value on the surface at the new point. F at x naught, y naught is the z value on the surface at the original point. So what's actually happening here is this is the actual retail change, delta z, on the surface. Now what's this equal to? Well, hopefully you recognize this as the total differential of z dz. Fx, remember, is the rate of change of the function with respect to x. So this is the rate of change of z with respect to x times delta x. So this approximates the change in the z direction coming from the change in x. And likewise, this approximates the change in z coming from changing the y. And so we can think of these epsilon 2's as being the error terms. And so really differentiability boils down to the actual retail change on the surface can be approximated by the total differential. And that'll do it for number 1.